All right, this next example is a kind of quick and easy example, so I'll do this one all the way in both cylindrical and spherical coordinates. That way you have at least one worked example of cylindrical coordinates. Okay, again, we're integrating a function, which these are a lot better for than volume ones. Okay, so E over the region E, which is below x squared plus y squared plus z squared equals 1. And above z equals the root of x squared plus y squared. Okay, what does that look like? Okay, this we should get to recognize this really well. I don't think Math 126 necessarily forces you to recognize that, but we should think of this as z equals r in polar or cylindrical. And what that means is that we start at 0. When r is 0, z is 0. When r is 1, z is 1. So we've got a circle of radius 1 at a height of 1. And then we've got a circle of radius 2 at a height of 2. And then, of course, we have all the ones in between, too, right? Like r could be all the decimal values in between. So what we end up with is a cone. And like you can think of this as the line z equals r, except it's rotated all the way around. So like one notable thing about this that we have to know is that angle is 45 degrees or pi over 4. Either side of that. This side is also pi over 4. Okay, so that's a cone. And then here's a sphere of radius 1. So what we end up with is this ice cream cone thing. We want to be integrating the function 3z in that region. Okay, let's do spherical first since our previous videos were all spherical, so we're on that track. Okay, so what actually happens here? This is actually cool. We're integrating, let's see, z is fine, so this is 3 rho cosine phi is z, right? And then we need a rho squared sine phi d rho d phi d theta. Okay, we've got 3 integrals. Rho, what's the maximum possible distance from the origin is 1, right? So rho goes from 0 to 1. And then phi is cool now. Phi actually is that angle that we talked about from the positive z-axis. So phi goes from 0 to pi over 4. And then theta, we're still going all the way around if we take cross sections parallel to the xy plane. So theta still goes from 0 to 2 pi. Okay, so it seems like spherical coordinates are perfect for getting little ice cream cone-like regions like this. Phi just takes care of it for us, the cone part. Okay, excellent. And then we just integrate. So let's see what happens. This is 0 to 2 pi, 0 to pi over 4. Let's clean this up a little. So this is 3 rho cubed cosine phi sine phi d rho d phi d theta. We'll integrate with respect to rho first. So 0 to 2 pi, 0 to pi over 4. This is 3/4 rho to the 4th cosine phi sine phi d phi. Sorry, I need to put in bounds still. So rho goes from 0 to 1. And then later I will need to integrate with respect to phi and theta still. Okay, putting in a bound of 1, I get 3/4 cosine phi sine phi. Putting in 0, I get 0. d phi, d theta. Okay, and I wanted to show you this part. There's a couple different ways to do this. I could do a u sub. That's idea 1. Or idea 2, I could, if I know my double angle identities really well, which I encourage you to do, sine 2 phi is 2 cosine phi sine phi. Or in other words, this thing is half of sine 2 phi, and that's quick to integrate. So I'm going to do it that way since that's probably not the way you thought of, just so you see something different. Might have been the way you thought of, but I think most of you would do that with a u sub, which is also fine. So this is 3/8 sine 2 phi d theta. Okay, so then I just integrate that 0 to 2 pi. This is 3/8 cosine 2 phi. I need a negative and I need a chain rule, so it's actually negative 3/16. Phi going from 0 to pi over 4. I still need to integrate with respect to theta. And then the nice thing about this is I don't need to know what sine and cosine of pi over 4 is. I just need cosine of pi over 2. Maybe that's overly lazy. But cosine of pi over 2 is 0. 0 minus negative cosine 0 is 1. So I get positive, should not be writing in highlighter, positive 3/16 d theta. And so that's 3/16 theta, theta going from 0 to 2 pi, which is 3/8 pi. All right, so that's with spherical coordinates. I get 3/8 pi there. Let's do it with cylindrical, because it's kind of maybe more calling out for cylindrical. At least that's what it feels like to me. I didn't, once we did the polar, it seemed very natural because phi went from 0 to pi over 4. But certainly before I tried that, I would have thought cylindrical. So let's see if we can do it that way. Need 3 integrals. The nice thing about cylindrical is I don't have to convert, so maybe this will be easier. I just leave that as 3z. 3z r dz dr d theta. And this part, that's nicer too. I don't have all that rho squared sine phi business, so that's good. All right, then z. Okay, so here's where it still looks a little bit like Math 126. Z is now going from this surface to this surface. That's fine. It's really going from, this is z equals r, to the root of 1 minus r squared. Not terrible. R is going, let's see. Okay, now we have to look at what region in the xy plane. So if we squish that whole ice cream cone down into the xy plane, or we think of its shadow, if we shine the light straight down on it, we get a circle in the xy plane, right? And we have to figure out what radius that circle is to figure out what region we're integrating over. What does that mean? That means we need the curve of intersection, and we see from the picture that it's going to be a circle. Curve of intersection of those two surfaces. So the way to do that is to do something algebraic. So if I have, let me call that equation 1, equation 2, and I'm just going to sub 2 into 1. If we combine them somehow algebraically, we should get something that satisfies both. So I get x squared plus y squared plus z squared is another x squared plus y squared equals 1. So x squared plus y squared equals 1/2. And this is a circle of radius. That's not how you spell radius. Radius 1 over root 2. Okay, so r actually goes from 0 to 1 over root 2. So note that was a little bit of extra work there. Otherwise, maybe this looks nicer so far. And then theta, we want that whole circle, so theta goes from 0 to 2 pi still. Great. Okay, then we're going to integrate, so 0 to 2 pi, 0 to 1 over root 2. Let's see, z integrates to 3z squared over 2. We need an r. Z is going to go from r to the root of 1 minus r squared, dr d theta. Plug that in. 0 to 2 pi, 0 to 1 over root 2. And then, let's see, we have 3 times 1 minus r squared. No square root because that was squared, over 2 times r minus 3 over 2 r cubed. And then we have to integrate that all with respect to r and theta. Let's just do a little bit more simplifying before we integrate. 0 to 2 pi, 0 to 1 over root 2. Let's see, what is this? 3 halves r minus 3 halves r cubed minus another 3 halves r cubed, so minus 3r cubed is what that is. dr, d theta. Okay, 0 to 2 pi. This is 3/4 r squared minus 3/4 r to the 4th. R going from 0 to 1 over root 2. Still need to integrate with respect to theta later. And then that's integral from 0 to 2 pi. Let's see, putting in, so r squared is 1/2. So this is 3/8 minus r to the 4th is then 1/4. So minus 3/16 minus 0 minus 0. D theta. So this is 3/16. And then integrating with respect to theta gives us theta. 0. Maybe I can write it better. 0, 0 to 2 pi. And then I get 3/16 times 2 pi, which is 3/8 pi. Okay, so same answer as the other spherical, so that's good. Which one was easier? I think, in my opinion, the cylindrical is harder because we have to do this clever thing where we find the curve of intersection. Maybe that's what you're more used to if you learned 126 really well. The spherical was nice because that pi over 4 for phi, 0 to pi over 4 gave us the whole region, and it felt natural, surprisingly natural, so that was good. So again, you don't need to necessarily have a preference, but that is how you do this in both cylindrical and spherical coordinates.